Okay, great. Let's start. So look, let's just review somehow everything that we should know by now, right? So again, what do we have? We have the following. So we already know what a probability distribution is, right? We've been talking about this for many hours, right? So probability distribution, write that again. Probability. Okay. A probability distribution P, right? So we've been talking about this for many times, hello? And we all know what a probability distribution is, right? So if we have a probability distribution, again, this is some function from the Borel sigma algebra to 0 and 1, set of the real numbers from 0 to 1, right? So this is just the probability that we have, okay? Now, since if we have some probability distribution on R, right? Right now we are talking about R, then we can define the CDF, the cumulative distribution function, right? And this is a function from the real line to 0 and 1, okay? And I told you that since we need to talk, we need the things to be more like, I don't know, understandable for us. We are not going to work with the probability distribution. We are going to work with CDF, with the cumulative distribution function, because this is a function defined on the real numbers. So this is something that we can work with, because you already had calculus and so on. So we can find some integrals and so on here, okay? Now, if we had that, and we're talking about R, then we can talk about two different kinds of probability distribution, right? So I told you we have discrete, right? And we have absolutely continuous. So two different kinds of probability distribution. For the discrete, we have the Bernoulli distribution, we have the binomial distribution, we have the Poisson distribution, we have the geometric distribution, we have the hypergeometric distribution, and so on. We have many distributions, right? For the absolutely continuous, we know now that we have the uniform distribution in AB, for example, right? So the uniform distribution in AB. We also have the normal distribution with parameters A and sigma squared, right? We also have the exponential distribution with parameter lambda, and what else do we have? And we have the Cauchy distribution with parameters, I don't know, theta and R. Let's call it theta and R. Okay, so this one is complicated. So I think we will talk about in the case when this is 1 and this is 0, right? And that's all that we know by now. We know that the uniform for the uniform distribution. So if we have discrete case, we can define something called the probability mass function, the PMF, right? The probability mass function, right? But if we have the absolutely continuous distribution, then we define the PDF, so the probability density function. And the probability density function is actually the one that we are going to use when computing any of the things that we want from these distributions, right? For example, in the case of the uniform distribution on any interval A and B, we have that the PDF is just the 1 over B minus A, right? In the case when X is between A and B, right? Do not forget that this means this is the indicator function, right? The indicator function. So it means that if X is between A and B, then this is 1. If X is not between A and B, then this is 0. Okay?
Yeah, but also for discrete and absolute, the PMF is only
No. PDF is only for absolutely continuous, right? On
PMF can be applied.
no, the CDF, right? So that's why I have here like the CDF big, big title here, and then I have this division here. So you can actually call the PMF discrete PDF somehow. This is the PMF. We can call it. This is not usual in English, but in Russian it is. So this is somehow the discrete PDF, right? But the discrete PDF is not a PDF, right? Somehow. So because what is a PDF, right? So let me go back to that. What is a PDF? A PDF is a function defined on the real numbers to the set of the positive real numbers, right? And such that we can find the CDF of a distribution like the integral from minus infinity to x of p of t dt, right? So this is, if such function exists, this p, this function, if this function exists, and this function exists only in this case, when we have absolutely continuous, right? Well, we actually say, if this function exists, then it means that this distribution is called absolutely continuous. And yeah, and we can compute the CDF in that way. And that function doesn't exist for the discrete case. Okay, good. What else? We have that. Okay, now for the normal distribution, we see that. Let me see here. So for the normal distribution, we have that the PDF is 1 over the square root of 2 pi times sigma squared times e to the minus x minus a squared over 2 times sigma squared, right? So this is the PDF for the normal distribution or the Gaussian distribution, okay? And we already talked that this function looks like this, right? So this PDF is the famous Bell curve, so something like this, the bell-shaped curve, right? And we know that this function is even. So if in this case, if a is 0, right? Let's say that a is 0 here, then it means that you can imagine that we have a mirror, right? So the same. So the function from minus infinity to 0 looks like exactly the same from 0 to plus infinity, right? It's like having a mirror, okay? Like, for the normal, in the case, yes, when a is 0, I mean, a can be any value. So what if a is, for example, 1? Then it's going to be just like this. So here in 1, what is going to be even in relation to this a, right? In relation to this a, the function is going to be even. Good. All right. Now, we talk about the properties of the PDF. And the first one, well, now this is the definition, right? But the main property of the PDF is that the integral from minus infinity to plus infinite of the PDF is 1, right? The integral from minus infinity to plus infinite is 1. Is this clear? This is very important. You have to understand why this is so. Okay. Look, the definition is like this, right? So it means that this, what is this? This is f of, so instead of writing x, we have to write plus infinite. So f of x, but the limit when x tends to plus infinite, something like that, right? So it means that this is the probability that this random variable is less or equal than minus that plus infinite. That is 1. The probability that this number is less than infinite is 1, right? So this means probability from minus infinity to x. This is the CDF. The probability from minus infinity to x. But if x tends to plus infinity, so this is like having the probability from minus infinity to plus infinity. So what is the probability that we have the number between minus infinity plus infinity? Of course, this is 1. Right? Good. And the second property, so all of this you already know. This is just, I'm repeating everything that I said the previous class. And in this case, we have that for any Borel set, right? So you can imagine that we don't have a Borel set. I mean, this is a Borel set, but we can just take it for some interval from A to B, right? For any interval from A to B, right? The probability that, let's use now random variables because I already defined what the random variable is, right? That psi belongs to A and B is going to be equal to the integral from A to B of the density, right? So it means that over here, this is the PDF, right? And this is A and this is B. So the probability that this random variable with such distribution belongs, so is here between A and B, is equal to this area, to the area here, to this area from here. So the integral from A to B of this function, right? So this area give us the probability that this random variable is between A and B. Okay, so this is what is written here. And yeah, and the same. Here, all of this is PDF. This PDF. Or you mean this, or what?
And the PDF number 1, which one for the uniform?
This is for the uniform, yes.
No, what I meant the first integration from minus infinity to infinity equals to 1. And what type of PDF are we talking about?
For every PDF. This is a property, so these are properties. So this is true for this PDF, for this, or for every PDF. If this is a PDF, this is true because this is a property of this function.
But then the graph, the symmetrical graph, is also a property of PDF.
No.
So it's only for one type.
That's for the normal. For the normal, okay? Not for every. So the PDF, it's not necessarily continuous, right? How does the PDF of the uniform distribution look like? You have A, you have B, it's like this. So this is the PDF for the uniform distribution, A and B. So the PDF is not like the CDF, so don't get confused with between the CDF and the PDF, all right? The CDF is kind of, I mean, the PDF is some special case of the CDF. It's a function of the CDF, right? So somehow, so these are different, and the CDF is more general because this is both for discrete and continuous cases, all right? Okay, so these are the properties. And then let me write over here. And then we had, yeah, sure. And then when we have the exponential distribution, right? We have the exponential distribution. For the exponential distribution, we know that that the PDF looks like this. So 0 in some moment here in alpha, in lambda, it's going to be like this, right? This is the PDF for the exponential distribution, and the function is, let me see, is PDF. This is 0, this should be lambda, yeah, lambda to the e to the minus lambda x. Now I'm not sure. 1 minus this? Let me check. I don't remember. So for the exponential distribution, we have. Yeah, this is correct. This is correct, my friends. And for every x greater or equal than 0. Well, greater than 0, greater or equal, the same. This indicator function, right? Indicator function, don't forget. Why do I write like this? Because I can write either this or I can do the following. If x is greater than 0, then this is lambda e to the minus lambda x. And otherwise, right, this is 0. This is the same, but I don't want to write it like this because it's long. So we don't need it. Hope it's clear. Okay. And for the Cauchy distribution, well, we have some density, and that's it. And then finally, we say that we have that what is a random variable. Finally, what a random variable is. And a random variable, again, a random variable psi is just a function from omega to the set of the real numbers. So if we have here omega, and we have here the set of the real numbers. So this is a function from here. The domain of this function is omega, and the range is the set of the real numbers. But we need that we need this function to be measurable. Measurable function. What is the meaning of that? It means that for every Borel set, we need that the preimage of B is an element of F. So here we have omega and F, and here we have R and the Borel sigma algebra on R. So we have two different measurable sets. We have a function between two different measurable sets. You already know what the measurable set is. A measurable set is a pair where we have a set and we have a sigma algebra on this set, right? So omega is any set, the set of chairs here, the set of, I don't know, books or anything, and we have a sigma algebra on this set, right? We know this. And then we have R, right? Any set, well, R is the set R, and we have the Borel sigma algebra, and the Borel sigma algebra, as you know, is the minimal sigma algebra containing all the open sets, right? And this is a sigma algebra. So we have a measurable set, we have another measurable set, and we have a function between these two sets. And we need this function to be measurable. The meaning of that is that for any B here, B, so for every open set, and not only, but for every open set or for every Borel set, the preimage sigma to the minus 1, sigma no, but psi to the minus 1. So this is going to be some set here, right? So this set here is psi to the minus 1 of b. This is the preimage of this function. This is a set, so look, xi to the minus 1 of b is a subset of omega, right? So the preimage of this is a subset of omega. And we need this subset to be an element of F, where F is the sigma algebra on here. And we know that F is just a set of subsets of omega, right? So let me remind you that this is a sigma algebra, which is a set of subsets of omega, right? If this is true for every b, for every Borel set, then this function is called measurable. So it means that not every function is measurable, right? So if we are talking about the discrete distribution, in the case of the discrete distribution, every function is measurable. In the case of the absolutely continuous distribution, not every function is measurable. So it means that not every function is a random variable. So a random variable, so a function to be random variable, to be a absolutely continuous random variable, it needs to be measurable. And finally, we have that, right? And then look, and then here, in here, let me write it with a different color. And here, of course, we had also some p, some distribution p here, right? Some distribution p. But and then if we apply this xi, so depending on how we define xi, here we will get a distribution generated by xi. So what is the meaning of this? This is here b, right? So this function is defined on the sets of the Borel sigma algebra, so on every b. This means this is the probability that xi belongs to b, right? And here, and this is equal to the measure of such omega from here. So look, here we are talking about this. Here we are talking about this. Here we are talking about like the process. So the probability that xi belongs to this b. And here, and now we're talking about omega. So we are talking about the sets from here, from this set. So the probability that of all omega such that psi of omega belongs to b. So what do we have here? We have p, this p is from here, look. So this p is the probability measure on this set, right? And this p with this function psi generates a probability distribution. So this generates this other p from here, and this p is this p, psi. So the yes. So if we change this, then this changes, and if we change psi, then this changes, right? So that is why this is the probability distribution generated by psi. If psi is different, then the probability distribution is going to be different. And let me show you that this is a probability distribution. This is not, right? So the probability distribution is defined on R. And if P is here, this is just a probability measure. Probability measure, probability distribution. The probability distribution is a probability measure, but every probability measure is not a probability distribution, because a probability distribution is a probability measure defined on the set of the real numbers. Yeah, maybe. It's good that we have colors because somehow we can. Right. Great. Now, look, we've been talking about probability distribution. We didn't have the word xi, the word random variable here, right? But now we can see that since this is a probability distribution, every probability distribution is generated by some xi. So now we can talk about the probability distribution of a random variable. And that's the meaning. It means this. The probability that xi belongs to this set B. So the random variable is any random variable. So we have a random variable, a random number or something. And we say, what is the probability that this number is between 5 and 10? Right? When we say, what is the probability that this number is between 5 and 10, we are talking about what is the probability that this random variable is between the set A and B, between this B. So it means what is the probability, so what is the measure, no, what is the value of the probability distribution in A and B, right? Maybe I'm doing more confusing everything, but, right? So look, they are different, okay? And let me write this over here. Big like. Sorry, B. Or, yeah, so this can be just A and B. So this P and this P are different. This is the probability distribution on R, some probability distribution on R generated by psi, and this is just the meaning of so this is like with words. What is the probability that blah 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 blah? So this is the meaning in the real world, in words. These are just words. So this is like saying, what is the probability? So no, this is the probability that psi belongs to A and B, right? So this is a function. This is just probability in words, the meaning, and this is equal to the measure. Now this is again a function, right? So this function from here is from the Borel sigma algebra to 0 and 1, right? And this function from here, so here we will write the probability of omega, such omega, such that psi of omega belongs to B. So here, this is the probability measure on, so this is a function from F to 0 and 1, right? So this is a function, probability measure. This is also a function. This is just like asking themselves, like ourselves, what is the probability of that? So these two things are different. They are equivalent, but they are different. The mathematical definition is different. Yeah. So do you have any question? No?
I have a comment that please have mercy on me.
What about the homework? Did you try to solve the homework? Maybe we'll have to reschedule the test for, because most of the test is going to be about this homework. So
not about like the first homework, like we have to do the first, second.
Yeah, but half of it, I think. So let's see. And now we can continue. So this is all that we had to know, right? So this is all that you should know by now. Okay, and I really think that we are not going to study everything that we have to study. We don't have time, really. It's amazing. But all right. So now what do we have to do? We have been talking about the probability distribution on R, right? Now let's talk about the probability distribution on Rn, right? So probability in grid, probability distribution on the space. So we've been talking about R, now we'll talk about the space, right? Any space of any dimension here. Well, this is almost the same. We have a little few differences, but it's almost the same. So what do we have to do here? First, we have to define the space, the measurable space in which we are working. So here we had that the measurable space was what? Was R and the Borel sigma algebra on R. This is for this case. For this case, of course, we will have what? The measurable space in this case is Rn and the Borel sigma algebra on Rn. Right? So for example, if a Borel set here is the interval AB, and then what is a Borel set here? Yeah, but so here we had segments like this, right? A and B. And here, if we are talking about the plane, then we will have something like this, right? Yeah, A, B, and here, yeah, A, B, and I mean, you got it. Like how to? No, this is not the best way to write it. Just a sec. A, B, C, D. So squares.
It's basically the same plane, X and Y. Now we just have a square, like not only AB, but A, B, C, and D.
Yes, because so here in this line in R, we have the Borel sigma algebra. So we have some B here. This is B, right? Some B, for example. And now if we are on the plane, then we have R here and we have R here. And the Borel set in this case is just the Cartesian product of this and this. So the Borel sigma algebra on Rn is just the minimal sigma algebra. If you remember this means minimal sigma algebra containing, right? So this is the minimal sigma algebra containing all such Cartesian products, B1, B2, Bn. Okay, and where, let's continue over here, for every I, Bi belongs to the Borel sigma algebra on R. So I will give you a break. It's just a second. So it means that, look, I am writing the Cartesian product of all of this, right? And the Cartesian product of this is just squares or a cube or something else like that. But I'm not writing that this is equal to this. I'm writing that this is equal to the minimal sigma algebra containing this. And that's different, right? So it's like when I had the Borel sigma algebra is the minimal sigma algebra containing all the open sets. I didn't say that the Borel sigma algebra are all the open sets. It's the minimal sigma algebra containing all the open sets. So instead of writing open sets here, I'm going to write this. Why? Because we don't need only this. We also need, for example, this, right? Or this. So we need all the possible areas on the plane, for example, right? Or all the possible figures on the space and so on. And the minimal sigma algebra containing this, so all the squares, is the sigma algebra that has all of these shapes like this. Yeah, the Cartesian product is the Cartesian product. I mean, you just, for example, the Cartesian product of this segment, so of this segment and this segment is all the possible points in here. So all of this area, all of this. Yeah, everything inside, right? Like AB is just the set of all the points over here, and this is all the set of all the points over here. Then the Cartesian product is all the points inside this, right? Okay, so look, I'm writing this sigma here because so what is the meaning of sigma? Let's say that we have some A. So we have omega, right? And we have A, right? So we have the sample space and we have a subset A. What is the sigma algebra, the minimal sigma algebra generated by A? Could you please tell me? So first we need the empty set, right? Then we need A itself. Then we need the complement of A. And we need omega. This is the smallest sigma, so we don't need any more. If we take out this is not a sigma algebra containing A. I mean, not only this, but any of these sets, if we take out any of these sets, this is not a sigma algebra containing A. That is why this is the minimal sigma algebra containing A. And this, we did this previous semester, right? Yeah, this is a subset. So this is the minimal set of subsets that contain A, and we can call the sigma algebra, right?
The definition of that semester here correlates with the definition.
Of course. So what is the minimal possible sigma algebra that we know? Hmm? Hmm? And what else? I mean, we have omega. We have a set omega. What is the minimal sigma algebra on this set? Is the empty set and omega itself, right? This is the minimal sigma algebra possible. Now, the minimal sigma algebra containing A is this one. And what is the biggest sigma algebra if omega is discrete or countable? So, like the max. It's a set of all the subsets. The power set, right? So for every set omega, we can have many different sigma algebras, right? We have the minimal sigma algebra, we have the maximal sigma algebra, and we have the sigma algebra generated by some set A, right? So I don't know, another example. I think that this is important. No. Okay, let's write the sigma algebra for omega. The empty set, right? Then we take the singletons. Then we take all the possible pairs. And then we take omega itself. No, this is just, this is the power set, right? Okay, now let's take the minimal sigma algebra containing the singleton of 1. No.
Sigma algebra containing 1.
So we have the empty set, we have the set, we need the complement of this set. What is the complement of this set? And omega itself. So this is the minimal sigma algebra generated by the set 1, right? So in the same way here, instead of writing 1, we are going to take all these possible squares, right? All these possible squares, but as you can see, we have the squares, but we also will have something else. And this something else are all these possible, for example, a triangle or actually any figure that you can imagine on the plane. This is what we'll have something else, right? Nope, because that's how many do we have, right? So that's the cardinality, not the set itself. Okay. So there are different ways of to write the power set, but I write it like this. Okay. So we have this. We have this. Okay. Okay. So look. And then we continue. So we need a function. So we define that a probability distribution is a function from the Borel sigma algebra to the set of the real numbers. Now, the probability distribution on here, on this case, is going to be a function from the Borel sigma algebra on Rn to the set from 0 to 1, right? So instead of taking all the possible open intervals, we are going to take all the possible shapes, I don't know, figures or something like that, volumes that we can have on the space. And for each of them, we are going to give them a probability, so a number from 0 to 1, okay? So we already have, so this is the probability distribution in the space. And for a probability distribution in the space, we can define the CDF. So this is going to be the n-dimensional CDF. Yeah. So we have n, right? Before we have just x. Now we have x1, xn. And what do you think is this? So again, what is this? Wait. What is this? The CDF. This is what? What should I write here by definition? No. So the CDF, what is the CDF? The probability from minus infinite to x. So the probability that the random variable is less or equal than x, right? So if we know this, how should I write, what should I write over here? Sorry, here is close, right? So we have the Cartesian product here. So I have to take the Cartesian product. So is this in words means the probability that, okay, let's forget about n. Let's talk about the two-dimensional case. We have two random variables, for example, temperature and density. No, density is not. Temperature and what else do we have besides temperature? I already forgot everything. Temperature and humidity or something like that, right? So we have two variables, right? And this gives us the probability that the temperature is less or equal than, I don't know, 10 degrees, and the humidity is less or equal than something. I don't know how to measure this, right? So instead of talking about one thing, we are going to talk about two things. And we care about the probability that the first is less or equal than something, and the second is less or equal than something. All right. For example, let's say X is the grade, the final grade for student 1. And X2 is the final grade for the student number 2. We can say X1 represents the average grade of the boys, and X2 represents the average grade of the girls, right? Then this means what is the probability that the boys are going to get average grade less or equal than 5, and the girls are going to get average grade less or equal than 10, or something like that, right? So we are talking about two different variables at the same time, right? So that this happened and this happened, okay? All right. So this is the CDF, and okay, let me give you some example here. Okay, maybe this is not clear 100%. So we have X and Y, and we can talk about the CDF of X1 and Y1 on these points, X1 and this is the probability from minus infinite to X1 and from minus infinite to Y1. Sorry, here is closed. Here is closed. Let's talk about, what can we talk about? I don't know, X and Y. Yes, X is the number of boys in the group. And Y represents the number of girls. Okay? So, for example, let's take here, for X1, let's take 5, and here 10. So, all these pairs of numbers, so all of this, for example, what if we are, I don't know, here? Here we have 3, and here we have 4. This point means that there are 3 boys in the group and there are 4 girls, right? Now, the probability from minus infinite to 5, in this case, is the probability that the number of boys in the group is from minus infinite to 5. Or the probability that there is at most 5 boys in the group. But we don't want only that. This is not the only thing that we want. We want at the same time this. So we want to know the probability that both the number of boys is less than 5 and the number of girls is less than 10. So the less than 5 is this, and for 10 is, for example, this, right? So it's this area. So this is the intersection. And this intersection, all this till infinity, all the points over here, in all these points, we see that there are less than 5 boys in the group and less than 10 girls at the same time. All right? So we need that to happen at the same time. So here, we have the probability that for n variables, that this variable can be anything, is less or equal than each of these numbers, right? So we can have here many values. And I can tell you number of boys, number of girls, I don't know, like I told you, the temperature and the humidity, and I don't know, I mean, many examples that I can give you right now because I don't remember, right? So this is exactly the same that we did before, but in this case, we just don't have one variable, we have n variables. Of course, we are not going to work with n, we are going to work with 2 or 3. Because to find this, we need to find the double integral and the triple integral, right? And you all know how to find these integrals, right? Double integral over some d, if we have here t and, I don't know, y, dt, dy. Since you know that from calculus, you know this, and you also know how to find the triple integrals, right? So if we want to find the, okay, I'm going too fast. Let me just, this is in 15 minutes, I will talk about this. So look, we have the CDF defined by this, like this. Okay, good. Now we can talk about the properties of the CDF, right? So the CDF before the CDF was a function how? Right, like this, right? This is the CDF when we are talking about one variable. Now we are talking about different variables. So how does it look like, right? Well, it's much more difficult to know, right? Yeah, so let's see the properties. So properties of the CDF. No, for n variables. For n variables, right? For 2, it's just a special case. So the first one, what was the first property for this one? It's not decreasing. Yes. In different words, we can say that the probability that we have a number in here is always positive. This is the meaning, right? Because this is the probability that this minus this is always greater or equal than 0, right? So this minus this is this. This is always greater or equal than 0. Now we have to somehow do exactly the same, but for n different variables. So how do we do that? So let me get back to the example when we were talking about a number of boys and number of girls in the group. Here we have x, here we have y. But let's do it a bit different. X and y. Let's take some, I don't know, say 2, 10, and here 3 and 9. So this is 9, right? Let's find this thing represent the probability. So this is f of, no, this is not f. So this is the probability that x belongs to what? 2 and 10, right? Between 2 and 10. And y belongs between 3 and 9. Right? Uh-huh. In words, it means this is the probability that we have between 2 and 10 boys in the group and 3 and 9 girls in the group, right? So this is the number of boys, okay? Number of boys and the number of girls. Right? Let's find this using the CDF. How do we find this using the CDF? And the person who tells me get 0.5 in the final grade. Using the CDF. Yeah. So we know this that I told you.
So what we should do is maybe we are using the old table that if we have x plus 1 up to extent, we have to probability from minus infinity to x multiplied by 50.
Okay. So what should I write here?
So suppose our f of x is gonna be equal to 10.
So f of 210? Or what do you mean? So look, we have here probability of something and we have to calculate it using f. Something with the CDF. We don't need the integrals, right? Just f. F. F of 10 is not defined here, right? Because f depends of two variables. Okay, f 10, 9. F 2, 3.
Then it's gonna be from minus infinity 10 multiplied by the probability from minus infinity.
Yeah, but wait, so that's it?
Yeah.
No, it's not.
Wait. No, of course not. So if we do this, we're gonna get the upper dot and the lower dot, and then we care about wait, 10, 9, and 2, 3.
Okay, so you have one chance. So tell me the answer right now, or Mihail will tell me. If you can tell me right now, you get the points.
And then we also have to include from 2, 9.
Okay, so this is okay.
No, sir. So I think that we need to say the following thing. So this is going to be f of 10, 9 plus f of 10, 3 minus f of 2, 9 minus maybe something like that because we have to include all the coordinates. If we're talking about the square itself, we need this coordinate and these coordinates because they're higher. If we minus from the higher to lower, it makes sense.
Okay, Mihail, do you see the mistake? Where? Here, 210? 210. No. No? You don't see the mistake? So you have one more chance to correct your mistake. Yeah, one more chance. What should we change here? You almost got it. What should we change?
Too much stress.
Here, what? So this is 10, by the way, right? It's written 10. So, where? Here? So here is plus or minus?
Then the second minus is plus. This is going to be 10 down here, then 10 here minus.
That's it?
No.
Well, you almost got it. You didn't. Look, what are you thinking here? You almost got it. Come on. It was. Look, what is this? F of 10, 9. This is all of this area, right? No, that's it. This is this area. We need this area. So this area minus this one. So this area, so f of 10, 9 minus f of 9, 2. Look here, minus n f of 2, 9, sorry. Yes, minus here, minus. Minus f of 2, 9 minus f of 10, 3. So this area minus f of 10, 3, yes, plus, because we 2 times we subtract this area, right? So plus f of 2, 3. No, because Mihail always so close. So no, sorry. I mean, you were really close, but don't worry, you will have more chance. So, do you see it? So it was. So if we want to find this area, we have to take all this area minus this one plus this one, because we already subtract this 2 times. So this is this. So the probability that is here is this, right? Now we can write this not using these specific numbers, but we can write using A and B. So the probability that we are in some, let me see, yeah, so the probability that we are in some A, B, and C, D, right? So instead, we'll have here A, sorry. So A1, so let's go A1, B1, and A2, B2, right? So the probability that we are in A1, B1, and A2, and B2 is just f of what? F of B1, B2 minus f of B1, A2 sorry, B1, A2, yes, minus f of A1, B2 plus f of A1, A2. And we can extend this. So this is just when we have n equals 2, right? So if we are talking about the plane is like this, but if we're talking about n, then we are going to say the following, and with this I will finish. So we need, so the first property, because this is what we wanted to say, the first property of this CDF is the following: delta 1 A1 B1, delta 2 A2 B2, delta n AN BN of f of x1, x2, and xn should be always greater or equal than 0. So it means that this area should be always greater or equal than 0, where each of these things, delta I of AI and BI, means of f x1, xi here, xn, this means f of everything, but instead of writing xi, we write bi. Bi minus f of writing x1, And we change this xi by ai. So we have ai xn. This triangle means this. So look, where's the difference? Here we have xi. Now let's just do the following. Instead of writing xi, let's write ai. Sorry, bi. Minus, instead of writing xi, we will write ai. You can, and it means that this from here, this is equal to the following. Delta 1 a1 b1, delta 2 a2 b2, f of x1 and x2. You can do it for this and you will get this. And this is the first property of 3. We'll see the others next lecture. So the first exercise, what do we have here? We have some CDF, right? And we need to find the PDF. Yes. And some probability. So the CDF is 2x squared plus 5x. Zero and 3, right? Mm-hmm. Sorry. Mm-hmm. Okay, so this is the CDF, and we have to find the PDF. How do we find the PDF if we know the CDF? So just the definition, right? So what is the CDF? The integral from minus infinity to x, right? This is the definition of the CDF. If the CDF is differentiable, then all that we need to do is this, right? I mean, we have to find the derivative here and the derivative here. This gives us just the PDF, and well, we have here the derivative. That's it, right? But this is possible only in the points in which this function is differentiable, right? In which points this function is differentiable? Well, in the points when where x belongs to this interval, right? So it means that, by the way, this is wrong because this is sorry. Here is if x belongs to 0 and 3, and if this is 0, if x is less than 0, and this is 1 if x is greater than 3, right? So this function, how does this function look like? Let's look at the graph of this function. So we know that from minus infinity to x, this is 0. Then what? If x is greater than 3, this is 1. And if x is between 0 and 3, then we have this curve here. And it should be so. What if x is 0? Then all this is 0. What if x is 3? What if x is 3? Then we have 9, right? And 2, 18 plus 15. So 33, right? So it means that this is something like this. This is the graph of this function. You can see that all the properties of a CDF hold, right? This is non-decreasing. The limit when x tends to plus infinity is 1, when x tends to minus infinity is 0, and is continuous from the right. It's actually discontinuous. So this is a CDF. This function, so what about if we want to find this? The first thing that we need to look is at the, well, we can look at the graph, right? And if we have this constant, just a line, it means that the density here is 0, right? So if x is less or equal than 0, then p of x is 0, right? If x is greater than 3, then it's going to be 1. No, wait, why 1? No, 0. This is the CDF. But from the CDF, we can look at the PDF. Right? Because all the possible values for us are between 0 and 3. If we have something like this, it's not possible for us to get this value, so the density is going to be 0. Now, what about x when we are between 0 and 3? In that case, we have this function. This function. And we know that this function is 2 squared plus 5x over 33. So in this case, p of x is just the derivative of f of x. So what? So 4x plus 5 over 33.
Suppose we have PPF, we want to get the PPF, we just differentiate. If we have the PPF, we want the PPF, we integrate.
Yes. Just like that, right? So look, that's it. So how do we write the PDF? Is 4x plus 5 over 33 and the indicator function. Here we have how much? Well, doesn't matter, right? So this is the PDF. Just like that, you know, I mean, it's not difficult. You only have to differentiate and you can find this. No. Why? No, of course not. This is some distribution. This is not any distribution that we know about. The uniform distribution is like we have a line here. This is not a line. This is like this, right? Curve like that. You cannot integrate the PMF. You can sum up the PMF.
So if I sum up the PMF, I get the CPF.
Yes.
And if I subtract, I get the CPF via PMF.
No, because the CDF is not going to be. So what is the CDF of an the CDF of a discrete distribution? It's like this. You cannot find the derivative of this.
So I cannot go back from CPF to PMF.
Yes, you cannot. All right. So we already found this. Good. Great. What else do we need to find? Let's see. Okay. Well, we can find. We haven't looked at the expected value and all of that, right? Okay, that later. Okay, and how? So we already have the CDF. What about the PDF? How does it look like? What do you think? Well, between 0 and 3, this is a line. So from 0 to minus infinity, this is 0. So this is 0, right? Here we will have also 0. Sorry, here, right? And between 0 and 3, we have this line, right? And this line is like something like that. So this is the CDF, this is the PDF. So sorry, this is the CDF and this is the PDF. So in the test, you will have something like this. You will be given with this, and I will ask you for to find the CDF and to draw the CDF and to draw the PDF. And I think we will have time, if we don't have the test next week, then we will have time to define how to find the expected value and how to find the variance. And then we will have to find the expected value and the variance of this. Okay. We are having it right now. I am not going to ask you things that we haven't talked about. That's for sure. Yeah, but so everything that I'm going to do during the test is to change this function. So instead of writing 2, I'm going to write 6, something like that. So the test is not going to be difficult if you know how to solve this. If you don't know how to solve everything from the seminar, well, of course, you're going to have problems. So we have this, and now we have to find the probability that x is between 1 and 2. I mean, we can talk about not x, but xi, right? Because I already told you. So we talk about the PDF, the CDF, but this is all of a random variable, right? So what is the probability that xi, so we say that xi has the distribution, right? Like this distribution, right? With this CDF and with this PDF, right? So this is xi. It's distributed like this. Now, what is the probability that xi is between 1 and 2? The one who tell me the answer gets 0.5 in the exam. By the way, guys, you can participate as well, right there, if you want. Gabriel critica his name. Using what? No, somehow, yes. 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 The integral from 1 to 2 of the PDF. Or, no, you got your points. Or what else? No. So, and for this one, also 0.5 points. How? Yeah, but what exactly? So he said the integral from 1 to 2, so the CDF of what? So just tell me exactly what do I need to write here. F of 1, 2 is not defined. We are talking about the line, R. So F only takes one value, X, one value, right? What? Let me just give you the point. By the way, the attendance, right? I completely forgot. So we have that, Mikhail, you have 1 point in the final. Okay. Very easy, huh? Okay, it's not difficult. So Jimenez is here. Mikhail is here. Coffee. Where's coffee? They no, or more. Yeah, it's not here. Monica is here. Wait, I gave him 0. Daniel's here. Rohan is here. Ashish is not here. Santiago is here. And Kritika is here. Okay. Now, yeah, that's it. I mean, is it this clear? If this is not clear, then we are screwed because this is the easiest thing that we're going to do today. So, do you see this? Please tell me that you do. Right. So let me show you this. So what is first this? So here. I told you that the integral from 1 to 2 of the density is the probability, so that the integral of from A to B of the density is the probability that psi belongs from A to B. So here we have 1, here we have 2. This area is the probability that psi belongs to this, right? And here is 2, here is 1. Here we have f of 2, and here we have f of 1. This distance give us the probability from 1 to 2, right? So let's find it. So the integral, sorry, the integral from 1 to 2 of the function. What function? What is the PDF? So it's 4x plus 5. 4x plus 5 over 33 dx. Right? So this is just the CDF, right? And the CDF is that function. So the integral of this is just that function, right? 2 x squared plus 5x over 33 from 1 to 2. You know this, right? Okay. So this is 3 times 4 plus 5 times 2 over 33 minus 2 plus 5 over 33. Huh? 2 times 4. No, we have 1. From A, B minus A. Where? I don't see it. So first We have 2 squared, so 4. Here we have 2, 1, and 1. I don't see it. Ah, yes, yes. So this is 2 here, right? So 8 plus 10, 18, right? Minus 7, 11 over 33. Right? Yeah, 1/3. That's the answer. Right? So it's very easy. Okay? So that's it. All that you have to know is to know a little bit about calculus. I mean, a little bit, not too much by now. Now next. So is everything clear? Yeah, okay, great. Now look, we had the CDF and we found the PDF. Now we have the PDF and we need to find the CDF, right? So the PDF is like this. So this is exercise number 2. Is a the sinus of 2x. Yes. When x is between 0 and pi, so a is between 0 and pi half. So this is the PDF. And now we have to find the CDF. But before finding the CDF, we have to find the value of a. Right? So what first question here is, what is a? So a is some number, of course. Which one? Of course, because I can tell you 5 is 1 million. Then this is not true, because this is not going to be a density. So a is given. A is some number, fixed number. We have to find it. How?
Can we make like an assumption? Don't you know that the integration of minus infinity of fx into t equals to 1? Know this assumption.
Right? No. Okay, now solve this integral.
Not on point.
I'll try.
Integration of sine is cos. So it should be, I forgot if it's possible.
Is cosine, are you sure?
Huh?
Are you sure that the integration of sine is cosine?
Wait, what? It's 10? Really?
What?
I forgot.
No, what I'm talking about now. No. So what is the derivative of sine?
Cos.
Okay, what is the derivative of the cosine?
Sine. No, cosine, sine.
No.
So if we left,
What is the derivative of minus cosine? Dear God.
that's what I meant. Rusty, but I'm there. It's gonna be.
So first of all, what do you need to do? Because you don't have cosine sine of x, you have sine of 2x.
It's gonna be 2 over.
Yeah, so you have to do change the variable here, right?
So we have to substitute. So this is gonna be like a and integration by substitution, something like that.
Yeah, please do it that way, because I want you all to understand what is happening, right?
Use calculator for that.
So just 2x, let's say that 2x is u, right? Then du is what?
Du is gonna be 2.
Right? Like this, right?
Yeah.
So please.
So we're gonna have the integration from infinity to minus infinity to sine u and du is equal to 1 over
Well, yeah, but just find this, and then we'll find a. Okay.
Yes, sir. So the integration of sine is going to be cos. So it's going to be
All right. You forgot. Yeah.
over 3x.
And here you can continue.
And now we are going here. Well, we can substitute 2x back here.
Yeah, I forgot something, by the way, right? So look, we are talking about minus infinity to plus infinity, but we don't have to talk about minus infinity to plus infinity. Why? Because this is defined from 0 to pi half. So instead of writing minus infinity, we have to write 0. So we have to write 0, and here we have to write pi over 2.
But will it hold the same value as 1?
Yes, because, so again, what do we have here?
Yeah, because we're talking about limits here. And
we're talking about integral, yes. So look, what is the integral from 0 to minus infinity? 0.
0. Ooh.
From 3 to plus infinity, 0. So the integral for minus infinity to plus infinity is exactly the same from 0 to well, in this case 3, but pi over 2, right? Exactly the same. So here you have to write from 0.
So it's going to be cos over 2. U is going to be over 2 minus, going to be minus cos of 0. This is going to be plus cos of 0.
So the cosine of pi over 2, what is that?
It's going to be, this pi is going to be 90, so it's cos of 90.
Look, don't think about 90. No, that's a really wrong way to think about this. You have to think about the graph. So the cosine is something like this, right? Here we have pi. Here we have 2 pi.
Yeah,
so here we have pi over 2. So it's 0, right?
This one, you can just cross it out 0.
0, yes.
And cos of 0 is going to be 1. So
yes.
it's going to be, answer is going to be 1.
Over 2.
1 over 2, of course. So we're going to get, just
there, yes. That a
1 over, 1 will equal to 1 over a, such that a equals to.
Exactly. So we found that a is 2, right?
We found out, I don't know integration.
Yeah, by the way, I don't know. I myself think about that in this way always. If you think about 90, I mean, if you think about the circle, so it's more difficult. I think. Think about this, and the sign is just like this, right? So, like
in my school, that we were given like a sheet for the test, and they were given us like the formulas like that, so we didn't have to remember nothing. So it's like if they say we were given this in our formula, so we just like go to the formula sheet, find and
no, just because you have to know what is. I mean, you cannot use your telephone or something during the test. So of course, if you don't know what is the cosine of, if you find the answer like this, this is okay, all right? I mean, this is 1. This is your point, okay, good. But come on, you have to know what is the cosine of pi over 2 is, all right? Huh? Pi over 2? Yes. By the way, yes. Because of substitution. So we have to divide this. So look, 2x, right? So here we have to multiply this by 2. So this is pi here. Yeah, thank you.
It's going to be pi here.
I mean, did you understand why? Yeah.
So this is going to be, this is too much.
What is the cosine of 5?
Cosine of 5 is going to be minus 1.
Minus 1, yes. 0.
So this is minus 1.
No,
minus.
No, again. Just again. Here we have pi.
Yeah, you're right.
Yeah, again, this.
So it's going to be, we're going to substitution. So it's going to be minus cos of 2x, right?
Well, minus cos of pi, right? Just write
Okay, so let me write it.
Yeah.
It's going to be minus cos. So instead of this, it's going to be x. X is going to be pi, 2 pi.
No, why 2 pi? We have pi.
Oh, yeah.
Pi.
Over 2.
Uh-huh.
And we said it's going to be minus cos of 0, right?
Mm-hmm.
So we already distinguished that this is going to be equal to 1 over 2. And it's going to be a plus. And then 2 pi is going to be, I'm just thinking of the circle, but it's going to be, I think, a minus 1.
Minus 1, yes.
Hey, you see I'm learning.
Yeah.
Minus 1 over 2, of course. So minus 1 and minus makes it a 1/2 here. This 1/2 plus 1/2 makes it a 1. It made no change. I should make a change.
Of course, we obtain 1. So A is 1. So if you obtain here 0, it means that something is wrong, for sure, because A cannot be 0. In that case, something is wrong, right? So A is 1. Good, great, thank you. So did you all understand everything? Okay. So what else do we have? We have to find now the probability, some probability, right? Yeah, the probability that this is between minus, okay, here. So what is the probability that psi between minus pi over 6 and pi over 6? Right? So how do we find this? We can use the CDF, sure, but let me before. So again, we found that the PDF is that the CDF, right? The CDF is what? Sine of 2x. No, the PDF was given. What was given? I already got confused. So yeah, the PDF here, PDF is sine of 2x in this from, right? So we know that this is the PDF, right? So now, how do we find this probability then?
Now we know.
Yeah, but we don't. Do we need the CDF? Do we need the CDF? Let me see. I just don't. Yeah, the CDF. Okay, how do we find the CDF? So we need to integrate what? From where to where?
From minus 5 to 6.
No. No. Do you want to find the PDF or do you want to find this probability? What do you want to find? No, no, no. Let's find the CDF. We need to find the CDF right now. I mean, forgot about this by now. This is C and this is B. We are trying to do the second part of the exam. No. Yes. From minus infinity to x. In which case, when if x belongs to, well, where? 0 and pi squared, right? Pi squared not but pi over 2. Otherwise, the CDF is what? So let's say that x is less than 0. Then the CDF is what? And let's say that x is greater than pi over 2. Then the CDF is what? 1. Right? Now here, we just need to find this integral. But since we are talking about 0, so we can forget about this minus infinity. It's going to be the integral from 0 to x. Okay, who wants to do it again? Ah, we already found that. No? Yeah, this is, what is this? So this is the minus 1 over 2, right? Minus the cosine of 2x. Yes? From 0, sorry, 2t. From 0 to what? To x over 2. Yes? Hmm? Yes, because we change here the variable. So we say that this is u is 2t, so t is going to be u over 2. So we change everything and divide it by 2, right? Now, what is this? So this is minus the cosine of x, right? Plus, here we have the cosine of 0, and the cosine of 0 is 1 plus 1 over 2. Here, right? Because we changed the variable here. Yeah, but we are finding the CDF. So we need to find from 0 to x, but x is less than pi over 2. Here, pi, you would get 1. So if you write here pi over 2, this is going to be 1. No, we are finding the CDF. We are not finding the probability. Yes? So look, the CDF is the probability of from minus infinite to x. So this is the integral from minus infinite to x of the density. Okay? So this is a function from x. So x is any value, right? And here we will get a function from x, not a number. So if we change this x by pi over 2, here, since this is defined, where is that? Not here. Over here is defined. Since, yeah, this is defined from 0 to pi over 2, the integral from 0, so the integral from 0 pi over 2 of this has to be 1. Yes? Yeah? Okay. Good. So we get this, and this is the CDF. That's it. Now we need to find this probability. So, yes. Yeah. So how much for the probability? Minus pi over 6. Sorry. Sorry. Plus. How much is this? Well, how much is this? What value is here? So what? By the way, did I do something wrong? Y minus cosine of x. I have written that here is 2x. Y 2x, y 2x. we have t. Because this is t. Wait, but if this is t, okay, this is 2t. We change this by u, so this is u, right? And here, here is 2x. U is going to be 2x. So here is not like this, sorry, but 2x. The other way, here we get 2x. Okay? This is what you meant before, or what? So yeah, so look, this is what? Let me write that over here. So this is 1 over 2 and 1 minus the cosine of 2x. What is this? Yes, like this?
No, it's just 1 minus cos squared 2x.
Like this, yes, yes. Yeah, this is true, right? Trigonometry. Huh? You remember?
When you just look at the paper that we're using like that.
So what is the sine of 2x, for example? Wait, no, sine of y minus 2. Yeah, this is true, for sure. Sine of 2x is, I forgot also. Yes. Right? And cosine of 2x is, well, you can see it from here, is, well, how much? Well, this is not enough. Here? Yeah, but we are dividing by 2, so. So here is something else. Anyway, don't forget about trigonometry. It's going to be useful here. So what is this? F on of this point. So this is the sine of sine square of p over 6, right? Minus, what is this value?
You write minus cos over 2x, minus cos 2x over 2. So if you plug 2x, 5 over 6, it should be 5 over 2.
Why? Yes. Yes, so this is, yeah, like that, right?
Yeah.
No, wait, but we have x here. I'm getting confused, man. So 6, right? And here, this is what? 0, right? This is 0. Why 0? I mean, the sign of this thing is 0? Yeah, then why this is 0? Why 0? Yeah, it's out of the range. So this is 0, right? So this is true in which case? If we are talking about this, if x is between 0 and pi over 2. Otherwise, this is 0. Look, 0 or 1. So that's it. So the sine of pi over 6, I don't remember. So it's just like that, right? So that's the probability. Okay, so we are done with this one as well. So is everything clear now? Yes? Great. Now let's start with something more serious. Okay, the third one, I don't know if we should do this one. No, let's what next class? We still have like 30 minutes first. So look, what is the deal? It means that we are saying that, so this is the third problem. The absolute value of psi is a random variable. Does it mean that psi is a random variable? Since I'm asking this, yes, no, it's not. Why? Why? Why not? Of course, if you tell me no, you have to give me some example, right? What example? So what if we have, look, let's say that we have the following space, omega 1 and omega 2, right? Let's say that psi of omega 1 is 1 and psi of omega 2 is minus 1. And let's take f, so the sigma algebra, just the empty set and omega. So we can see that this function is not measurable. So psi is not measurable. Why? We say that a function is measurable if for any Borel sigma algebra the preimage is an event, so it belongs to this, right? Now, what is the preimage of 1? Is omega 1. The preimage of 1, so look. Yeah, it's okay. We have only two elements, omega 1 and omega 2. And we have the real line, but we have only 1 and minus 1. This here and this here, and this is psi. The preimage of minus of 1 is omega 1. So the preimage of this is clear. This is 1. The singleton of 1 is omega 1. But omega 1 is not part of f, of this f. So this is not a random variable because this is not a measurable function. Right? Now, what if we have the absolute value of psi? So this is always 1. Right? So what is the preimage of 1? The whole space.
Because it was modular before.
Right. So yes, because we only have we only have 1. So the preimage of this is the whole space, and the whole space, you can see, is an element of f. So this function is measurable because we have only two options. Or well, no, yeah. So here we in that case, omega 1, we have omega 2, 1. So everything is just go to 1. So for every possible Borel set B, we have only two options. Maybe B doesn't contain 1. If B doesn't contain 1, then for this B prime, what is the preimage of this B prime? The empty set, right? And the empty set. But if B contains 1, so B2 prime, for every B that contains 1, the preimage of B2 prime is omega. So we can see that this function is measurable because every preimage for every B of the Borel sigma algebra is an element, is an event, right? So if you understand this, then so this is an example of what is a measurable function, of what the preimage means. That the preimage of every B should be here. In this case, the preimage of this is omega 1, and omega 1 is not here because we didn't want to be here. If F is this, so the power set of this, then this is a measurable function, xi. But since the sigma algebra is different, then this is not a measurable function respective to this F, right, to this sigma. All right, this was exercise number 3. Let's continue. Exercise number 4. And this becomes more interesting. Right? Now, we have some PDF, and we have to find the CDF. We have the Cauchy distribution with parameter theta n x 0. So, minus, right? Plus x minus x squared. Yeah. We have this probability distribution. This is the Cauchy probability distribution with parameters. So this is the Cauchy probability distribution, right? With parameters theta n x 0. We have to find, and this is the PDF, right? Now we have to find the CDF. To find the CDF, all that we have to do is to integrate from minus infinity to x of theta over t squared, theta squared plus t minus x 0 squared dt. And this is going to be the answer, right? So who can find this? Who can find this integral? Come on.
I cannot give you guarantee.
Okay, but before that, right over here, I just need all of you to know what is the derivative of sine. Seriously, the derivative of sine.
So dy over dx of sine is going to be cos.
All right. Of cosine.
It's going to be minus sine. Ah, you see it?
All right. Of tangent.
Oh, no.
Tangent. In English is tangent, right? Tangent.
What is it? Huh? 1 by what? Okay, can you say cos squared? 1 over cos squared. Fine sine.
No, the
Fine tan. Sine.
okay.
1 over 3 probability.
Yeah, is that true? Right?
True?
Yeah.
It's 1 over cos squared.
Cosine. Okay.
And of course.
And finally, what is the derivative of the arctangent? How is that in English? I don't know.
Arctan?
Arctangent. How is arctangent? Is it correct in English?
What's arctan? Oh, okay, arctan. Okay, I got you. Arctan X.
Well, guys, what is it?
1 by what? 1
Plus x squared. That's it. We need this, right? Right? Because we have something like that here, yes?
Where's the sun, where's the clock?
Yeah, well. Okay, we need this. Yes? So,
Yes, sir.
okay, using this, how do we find this? So we already know that. We can just. So what do we need? We need this to become 1, right? Yeah, that's it. That's all that we need.
No, so we assume that this one is the x squared.
Yeah, so let's say that that this is u, right?
Okay.
So we need to change this variable. So this is going to be u. U is going to be t minus x. So du, just dt, right?
Because we see this as a constant, right?
Yeah, this is a constant. This is some number, given number. Okay. All right. So you can say that this is equal to what?
Can we substitute 1 already? Can we just substitute, or we don't know that yet?
No, wait, just u, right? Every time when. No, so here we have x.
This is going to be
Du, right? Okay, what else do we need to do now? We need this to become 1, right? So we need to divide all of it for theta square. So this, here we have theta square and 1 over theta square. Yes?
both sides, yes, sir.
In that case, here we will get 1. Yeah?
This is going to be 1. So
Just
we're going to have over theta squared here soon. We can take it out. It's going to be 1. Yeah.
or we can just, yes, we don't need to do this actually. We can just, no, we need to do that. Yeah. So what do we get in this case? So we multiply this by all of this. So we get 1 plus u squared over theta squared.
Well, down here, it's going to be pi squared over theta squared. It's going to be 1 plus squared over theta squared. And here it's going to be better than minus power of 1. What do you mean what? You take this and then squared, and then 1 over theta. 1 over theta is same as theta to the power minus 1.
Okay, good, great. And what do we know now? What do we do now? So we can again just change. We need this to be some x. So let's say that all of this is equal to, so that u over theta is equal to z, right?
Maybe that's squared.
Yeah, then this will be what? So look here. First of all, you will have pi squared 1 over pi squared times theta. Yes? Wait. Yeah. Why pi squared? By the way, why do you have pi squared? Ah, here is pi. I think I make a mistake. Yeah, here is pi. Sorry, not square. Yeah. So we have this integral from minus infinite, and we are doing this, changing this. right?
But can't we also eliminate this by saying this is not going to be here, it's going to be 1?
We already did that.
Oh, yeah, yeah, I agree with you.
So this is gone. Now we have this, right? This is all du. Now
Shouldn't it be over theta here? Pi over theta, because here's only 1 and here's 2. Therefore, if we eliminate, it's going to be 1 and here's going to be over theta, not multiplied by theta. Because you see theta squared here. So if it's squared, means if we eliminate here, here remains 1. So it's going to be theta, pi over theta.
yeah, but theta.
So it will have to be pi over theta maybe here. So it's going to be theta over pi again.
Yeah, it looks like that, but why? Just
because
yeah, why?
Because you see, if it's pi divided by theta squared and then multiplied, and on the top here it's theta to pi.
No, we don't have theta squared here. Because you are multiplying to this one, not to this one. So this is 1 over pi times theta. So you are multiplying A, B, C. You don't multiply by this and by this.
Yeah.
You multiply only by 1. So theta is to this one, right? Okay. Now.
Then it's going to be 1 over 1 plus d squared. But then, okay. So if we integrate this, we're going to get.
Wait. And what do we have here? And what do we have here?
Not ABC, but close, x and minus theta.
No, not x.
Not x, of course, because we changed it.
Yes.
X squared. Oh.
Well, you got it.
Yeah, it's fine.
Anyway, but wait. Just wanted to get confused. That's okay. Wait. Now.
So it's going to be over theta?
Yeah.
This will be from arc 10.
Yes.
So it's going to be arc 10 of z from x theta to minus infinity.
You forgot about pi.
Yeah.
By the way, we yeah, we would have another theta and this goes, right? Yeah, we just changed it.
No, we changed it.
We had x and then we changed it by u. So with this, I understand, but we already changed by that. So we had t minus x, and we did like this is u, right? And now u, we have again. So here, this is u, by the way, not x, right? Or u. Yeah, yeah. Thank you. So, what's the answer?
The most important 1 over pi. Oh, 1 over pi.
Yes, 1 over pi times. Now, arctangent of what?
Well, if I'm not mistaken, the arctan of
u, and u is x minus, no, sorry. Yes, x minus x0 of x minus x0 over theta. So this value minus the arctangent of minus infinite. And the arctangent of minus infinite is
0.
No.
1. Between.
Okay, how does the graph of
I know,
of tangent look like?
This. Okay, this I know. Something like this.
Like this.
Yes, sir.
What do we have here?
90 degrees or pi. Pi by 2. Pi by 2. Yes.
So.
And here's minus pi by 2.
Okay, so minus infinite of arctangent. This is tangent. by the way, and arctangent is going to be like this, right?
Oh. Yes, sir.
So when this tends to minus infinity, this tends to
Minus pi over 2 by x squared condition. Yes. Yes.
yeah.
So this will be here minus, what for going to be 1 over pi. Is it minus? No.
Minus pi over 2. So plus.
It's going to be 1 over pi multiplied by minus pi over 2. And then, of course, close the bracket. Therefore, this will be pi. This can go out. This is going to be 1/2 here. This whole thing is going to be plus 1/2.
Yeah, that's it. This is the CDF. This is equal to f of x. So this is the CDF of the Cauchy distribution with parameters theta and x0.
Yes, sir.
That's it.
Easy.
Yeah. So let's think about, so is it clear for everyone? Yes? Now let's think about this graph, the graph of this function. So this is the CDF. It means that somehow it's between 0 and 1, right? Yes? So this is a bit confusing that way. So let me write that again. 1 over pi. Here we have the arc engine of x minus x0 over theta plus 1 over 2. So let's look at the graph of this function. What if here we have x, here we have f of x. What if x is equal to x0? So here, for example, we have x0. In this point, the function is going to be what? One over two, right? Because it's the arctangent of 0. The arctangent of 0 is 0. And so this function looks like this. For some given theta, and and for this x0. Now, what if we don't write theta, but let me change this theta by 2 times theta? How does this graph change? What do you mean by that? So here we would have to write 2. So slower, right? Yeah. And if we divide theta by 2, then we will get something like this. Sorry, wait. Okay, so so you can see that we actually don't have a CDF. We have a family of CDF, right? Because it depends on the value of theta, right? And if we change this, so if we have a new one, then of course here we will have this value, and it's going to be something like this, and so on. So you can imagine all the family of functions here. Now let's do the following one. Oh yeah. Wait. What do we have? What is the next one? Let me see which one we have for the next. Yeah, I mean, this one is easy. So let's do this one and we'll finish. As far as I remember, we finished at 55. 55. I've been studying here for 8 years. I do know very well at what time we finish. So now we have the gamma distribution with parameters 1 and 2. This is x e to the minus x for every x which is greater than 0. Yeah, am I writing this right? Yeah, so we have this, and we have to find, so this is the gamma distribution with parameters 1 and 2. Gamma distribution with parameters 1 and 2. So the gamma distribution is very general, all right? So from the gamma distribution, we will get the exponential distribution, and we will get the chi-square distribution, and many others distributions. So the gamma distribution is very important. But we are not going to study the gamma distribution because if we want to learn about the gamma distribution, we have to think about the gamma function and the zeta function and so on. And of course, we are not going to talk about that right now. Yeah. So, well, let's find the integral, right? From minus infinite to x of t e to the minus t dt. This is f of x. Okay. Yes.
Oh Lord, I don't remember that. Integration by parts, it's something like u d. I forgot integration by parts.
Okay, let me help you here a bit. So, what do we know? We want this t to be out. Yes, so let's say that u is t, and dv is e to the minus t, right? Mm-hmm. So du is going to be dt, and v is going to be minus e, wait, minus t, right? Wait, uh-huh. Good. We already know this. Then
so you have to do u multiplied by b.
No, by b, by v. U times v.
It's going to be like u multiplied b minus
the integral
of v du.
Of v du. Yes.
All right. So
no, it's not. Well, okay, let's see. I don't know.
Around.
Continue, and we will see.
So if you have u, so it's going to be follows that t multiplied by minus e to the power of minus t minus the integration minus e minus t will have du equal to dt. So
Don't forget about, we have here minus infinite, and here we have x.
okay, so now we want to integrate this part, and integration of this is going to be e to the power of minus t. Yes.
Mm-hmm.
So this is going to follow, we're going to have t multiplied by minus.
By the way, here this is from minus infinite to x, right? Don't forget.
Yes, sir. And it's also going to be minus x, and here minus is going to be also e minus t from minus infinite to x. So I think we can group like terms. So this is like term, and this is like term. So it's going to be e to the
Minus, okay.
minus t, take it out. This is going to be a minus.
Wait. Find this and find this. It's better, okay? So let's find this. So when we have x, so this is going to be just. So when we have x minus e to the minus x, right? We have x. When we have infinity, then we will have here infinity, so this is going to be 0, right?
How come? It's going to be positive infinity.
1.
Because minus infinity to minus t is going to be minus e to the power of positive infinity.
Yeah.
Maybe it's equal to 0. Maybe it's going to be.
Wait, so what's the deal here? Something is not good. VU minus g minus infinity to x.
The indicator function is only for x-rated.
Huh? So this is minus what? This is, but
This is going to be minus.
let me check. Where do we have the mistake here? Ah, this is from, wait, why? Ah, yes, of course, because this is not from 0. Because this is when x is greater than 0, then this is from 0. 0 and 0. Yes, of course. 0 and 0. Right, because we are integrating for these values.
Yes.
Now everything is okay.
Minus 0, this is whatever. So it's going to be e to the power of 0. So it's going to be multiplied by, so this is so this is going to be all zeros.
Yeah, but not this one. This one is when we have x. Okay, so minus x e to the minus x minus 0, then minus
e to the power of minus x.
Yes.
We can group like terms.
Wait. And what about this one? This is 0. Yeah. So this.
It's going to be plus 1. Where's the ratio?
Minus 1 here.
Yes.
So.
No, there's no like terms anymore.
So we can have that this is equal to what? Well, just minus x e to the minus x minus e to the minus x plus 1. And this is the CDF for the gamma distribution with parameters 1 and 2. Right? So we can write this better, like e to the sorry. And that's it.